Section 1.4, inverse functions. The definition of an inverse function is given a function f with domain D and range R, the inverse function of f, if it exists, is the function f to the, we write to the negative 1, but really that indicates the inverse. That does not actually indicate an exponent of negative 1. With a domain R and a range D, such that f inverse of y equals x, if f of x equals y. This function maps the inputs to the outputs. Okay, if the original function f, if f takes our x values to our y values, okay, then f inverse maps our y values to our x values. Okay. It does the inverse. It does the opposite operation that the function f does. The way to check this, okay, by definition here, if f inverse of f of x, if we compose the two, we get the identity. That is, if I start with the point here, map it over here, well then f inverse should take that point right back here. But that should work for every point, so we can compose them and check. That would be true for all x in D, or f of f inverse of y equals y for all y in R. That is, f inverse will take a point here over here, well then the function f should then take it back to the same point for every point. Now a function has an inverse. Okay, the function is invertible if it is a one-to-one function. So the definition of a one-to-one function is that if f of x1 and f of x2 are not equal, then the inputs, its corresponding inputs, x1 and x2, are not equal as well. Recall the definition of a function dictates that it has one output per input. That is, every input has exactly one output. A one-to-one function has one input per output. That is, rather than saying every x has one y, we say every y has one x. Okay. And we can determine if a relation's a function using the vertical line test. So here we can use the horizontal line test to determine if a function's one-to-one. The horizontal line test says that a function's one-to-one if and only if every horizontal line intersects the graph of f no more than once. All right. Well, if I don't have a horizontal line here, but I'm going to draw them, okay, at least in the air. Would any horizontal line I create, would it ever cross the graph more than once? Well, the answer is yes. If you can imagine this right here. And I say cross, it touches. It intersects that graph. So there's actually several places where it hits twice. Okay. It looks like every integer. Every integer that will happen. So this one is not one-to-one. Now for part B, same idea. Horizontal lines, never crosses more than once, so this function is one-to-one. Now, a problem-solving strategy to find an inverse function, because we were checking that with graphs. Okay, we will use that tactic several times, but to find it algebraically, we can solve the equation y equals f of x for x, and then interchange the variables and write y equals f inverse of x. I'm going to write this a couple of different ways. So first, we will go ahead and take the function y equals f of x, which will be 3x minus 4. If we solve this for x, go ahead and put all the steps out. Y plus 4 equals 3x. Dividing by 3, we have that x equals y plus 4 over 3. This actually is an equation that tells me how I can find the input given an output. If you tell me a value of y, I could say, well, add 4 to it, divide by 3, that'll be the x value that would have gone to that value. So this is actually one way to write this is f inverse of y equals y plus 4 over 3. Now the interchanging variables part is not really necessary. However, if we want to graph the two functions on the same axes, we need to interchange this and write f inverse of x equals x plus 4 over 3. Now, the original function had a domain of all real numbers and a range of all real numbers. When you find the domain and range of the inverse function, you interchange the inputs and the outputs, so the domain and range switch. However, in this case, obviously it doesn't really look like they did because they were the same to begin with. Now, the last part that we want to do is verify f inverse of f of x equals x. Okay, so f inverse of f of x equals x. F inverse is x plus 3 over 4. F of x is 3x minus 4. So we're going to take f inverse of 3x minus 4, which is going to be, let's keep this separate, 3x minus 4 plus 4. There's my input. Now this will be 3x over 3, which is x. And since that is x, that tells us, that guarantees that algebraically these two are inverses of each other. Now this was all about verifying. That was really not part of our answer, but it is good to know. Now, for a graph of a function, we can sketch the inverse by sketching the line y equals x, that reversing the variables idea. If we sketch the line y equals x, then we can use symmetry. So if x equals y, y equals x, there's the line y equals x. So we can sketch the inverse by reflecting it across that line. All right, so the original function had the points -2, 0, -1, 1, the point 0, 2, now let's see the point 2, 2, or actually let's not use that, it's not 0, 2. So the function f inverse should have 0, -2, 1, -1, and 2, 2. We interchange the x's and the y's. 0, -2 will be somewhere in this vicinity. 1, -1, 2, 2. That would be my inverse. A graph of that using symmetry. Now, the domain and range of f inverse, I want to start by saying what the domain and range were of the function f. The domain of f was -2 to infinity, and the range was 0 to infinity, including those. So f inverse, the domain is 0 to infinity, and the range is -2 to infinity, because we're interchanging those. Now we've said that the only time that an inverse exists is when the function's 1 to 1. So the next question is, what happens if the function's not 1 to 1? Well, in that case, we actually restrict the domain. We choose a subset of the domain that is in fact 1 to 1. So if we consider the function y f of x equals x squared, this function's not 1 to 1. However, if we restrict our domain to 0 to infinity, then it is 1 to 1 and it has an inverse. So let's consider this function, f of x equals x plus 1 squared. First, we're told to sketch a graph and use the horizontal line test to show that it is not 1 to 1. All right. It's not perfect, but it will do for now as a sketch. Continues in that pattern. And then we've also got something like this. So there is the function, well, that's the function x squared. x plus 1 would be shifted to the right one, which will not actually change anything, or to the left one. So even if I shifted this around, this is the parent function, but if I shift it, okay, let's go ahead and do that here, just so we can say we've done it. So negative 1 would be 0, 1, 1, 1, 4, okay, so f of x equals x squared. This is g of x equals x plus 1 squared. This function is not one-to-one because, for instance, we have two x values that have a y value of 1. So it's not one-to-one. Now we're going to choose a restricted domain. We're going to restrict this down to negative 1 to 0. So negative 1 is 0, 0 is 1, 1 is 2, 3, 4. Now in this case it is one-to-one when we restrict the domain because no horizontal line would ever cross twice. We've taken one of the branches of this off. All right, let's determine our domain and range. This is for f. The original function here, the domain is negative 1 to infinity, and the range is 0 to positive infinity, which means that f inverse will have a domain of 0 to infinity and a range of negative 1 to infinity. Now we want to find a formula for that. We have the graph, or a sketch of it at least. I want to find it algebraically. So this was f of x equals x plus 1 squared. Let's solve this for x. First we take our square root. So the square root of y equals x plus 1. Subtracting 1. We have square root of y minus 1 equals x. So that f inverse of x, I'm going to go ahead and perform my change of variables there. Inverse of x is the square root of x minus 1 on the interval 0 to infinity. All right, next we're going to return to trigonometric functions to talk about inverses. The inverse sine function, sine to negative 1 as is written, or arcsine, and the inverse cosine are defined on the domain from negative 1 to 1. And as you can see, the idea, we've switched our variables. If we took the sine of both sides, we'd have x equals sine of y. X equals sine of y. And it's restricted to negative pi over 2 to pi over 2 for sine inverse, and 0 to pi for cosine, because those are the easiest intervals to make them to see a whole period and to be 1 to 1. Inverse tangent has a restriction of, or a domain of negative 1 to 1. So here, negative 1 to 1. This one is infinity to negative infinity to positive infinity. Okay, and we have these restrictions on our outputs. But the big thing we're concerned about with them being 1 to 1 is actually our domain restrictions. So keep those in mind. Arctangent, okay, and cotangent inverse do not have restrictions. And then the cosecant function has a restriction for being greater than or equal to 1. Now here are the graphs of those functions on those respective domains. So arc sine and arc cosine look a lot like the original tangent function, whereas tangent looks different. Okay, it actually has a horizontal asymptote. So you can kind of see that some of the characteristics switch. Asymptotes, vertical become horizontal, horizontal become vertical, as well as some of the periodic behavior, the ones that were let's not chase that. All right, so some of the characteristics certainly do change here. Now, what we want to do is evaluate a few expressions. The first is arc sine of negative root 3 over 2. Now, what something like this is really asking is, what is the angle that would produce a sine of negative root 3 over 2? Triangles are the way to go. What angle would make a sine? Now, that's a y value. So that would be this right here. That distance being a positive root 3 over 2, or if we're thinking about that point, negative root 3 over 2. What angle would give us that? Well, based on that chart we worked with. Oh, let me also remind us that our angle must be between pi over 2 and negative pi over 2. Well, that angle would be a negative. Well, I might say, let's see, if we go, that would be 6/3. That's 5/3 pi. That's bigger than pi over 2. So what I have to say is that theta equals negative pi over 3, so that it lands between those two endpoints. Now, keep in mind the domain restrictions as we work with these. Now, part B, because there is no domain restriction on tangent, that means it's 1-to-1. It is 1-to-1. If you go back and look at the graph, horizontal line test passes. So this will be negative 1 over root 3, which is negative root 3 over 3 if you'd rather write it that way. So that is because tangent is 1-to-1. So as tempting as it is, that does not work for part C. Okay, it looks like 5 pi over 4, and the answer is no, it does not work. So let's draw a triangle. First, cosine of pi over 4, or 5 pi over 4. Cosine of 5 pi over 4 is similar to that'd be similar to negative, or actually positive. All right, so let's just write this over here. Similar to pi over 4, except that it's going to have an x and a y that are less than 0. So then cosine 5 pi over 4 is root 2 over 2, but it's negative. And the inverse of that, okay, so because cosine is the output is between 0 and pi, looking for a negative root 2 over 2, that would actually be 3 pi over 4. Cosine inverse of negative root 2 over 2 is 3 pi over 4. Because our x value would be the same over here, or actually our x value would be the same here, and since we're restricted on this half of our circle, it's got to be 3 pi over 4. Same idea for this next one, our last one. Cosine of 2 pi thirds is right here. If that's our theta, then our cosine is going to be similar to pi over 3. go ahead and add this in there. All right, so if it's pi thirds, then it's going to be 1/2. Or it's our x value, so it'll be negative 1/2. All right. And then if we go to look at negative 1/2, the angle that gives us that between negative pi over 2 and pi over 2, that's going to have to be a negative pi over 6. Negative pi over 6. So that's our answer to that question. All right, that brings us to the end of this section on inverse functions. Okay, and we've of course got some trigonometry to work with ahead of us, so that's it.